Today we'll look at the electric fields of conductors. And recall that in a conductor, you have the valence electrons detaching from the core of an atom, and they move around quite freely. Whereas with an insulator, the electrons are not free to move around. So this conductor is initially in electrostatic equilibrium, and as you can imagine, all the charges cancel, because if you had some excess charge, you're going to get a shock if you touch that metal. Now suppose we charge this conductor, such as by induction or grounding. These electrons are going to want to get away from each other as far as possible. So what happens is that the excess electrons spread out and they reside on the outer surface of the conductor, as shown here. So the mutual repulsion of all the charges on the surface of the conductor eventually creates a state of electrostatic equilibrium, which is reached quite quickly. And for uniform shapes like spheres and cylinders and planes, you're going to have a uniform charge density and an absence of an electric field inside the conductor. So if we suppose this here is our conductor, and it has a thick surface, so it's a thick shell with a cavity inside, well, inside the body of that conductor and inside the cavity, the electric field is zero. So as you can imagine, the electric fields due to each of those charges are going to cancel each other out. And in non-uniform shapes, you'll also have an absence of an electric field inside a conductor. And this is best visualized if we apply an electric field outside the conductor. So in this case, we're going to choose a uniformly charged infinite plate that's much larger than the distance between the plate and the conductor. So if we choose a point in the middle of the conductor, well, this electric field is going to be uniform. So remember that it's going to be sigma on 2 epsilon naught, where this plate is sufficiently close to the conductor and sufficiently larger. So what we're going to have is an electric field vector that looks something like this. Now, in the presence of this positively charged plate, more electrons are going to be drawn towards that positive charge. So that's going to leave a positively charged region on the other side of the surface, and therefore this imbalance of charge is going to result in an electric field that's going to act in this direction. So at this particular point, you're going to have the positive charges have an electric field that points away from the positive charge, and the negative charges will have an electric field that's in the direction towards those negative charges. And if you sum up all the electric fields due to these charges, you're going to have a resultant that acts in this manner. So therefore, you're going to have the electric field due to a superposition of all these charges, cancelling the electric field due to this positively charged plate, and thereby an absence of an electric field inside the conductor. And as a consequence of electrostatic conditions, well, you're going to have the electric fields due to these charges in a tangent direction to the surface, cancelling each other out. So as a consequence of electrostatic equilibrium on the surface of the conductor, you're going to have these electric field vectors from that external electric field being perpendicular to the surface. So for example, if we draw an electric field line from here, it's going to bend like this, such that the electric field vectors are going to be perpendicular to that surface. And another one that comes from here will look something like this. And on the other side, you're going to have it again being perpendicular and bend away from the conductor. Okay, so that's what the electric field is going to look like, with perpendicular components to the surface of the conductor, as a consequence of electrostatic equilibrium on the surface. So another electric field line is going to look something like this, and in the middle it'll look something like this. And you get the idea. Now that we've established that the electric field inside the body of a conductor and inside the cavity is zero, then the work required to move a charge between 2 points inside the conductor is also zero. So remember that the electric field is minus the derivative of the electric potential with respect to the direction. So if we choose some surface inside this conductor that looks something like this, well, because the electric field is zero throughout the conductor, so if I wanted to move a charge between 2 points on this surface, then the change in potential with respect to that direction is zero. And consequently, any surface within the conductor is an equipotential surface, or a surface of equal potential, because this gives the potential is constant. So even in the presence of an external electric field, this condition holds, because recall previously, we found that when I have an electric field line that's close to the conductor, it's going to bend near the surface of the conductor to maintain electrostatic conditions on the surface of the conductor. Okay, so the electric field line is always perpendicular to the surface of the conductor. Today we'll look at the polarization of conductors. So suppose we rub the glass rod here with a silk cloth, so we strip off some electrons and we're left with a positive charge. And if we bring this near a conductor, well, that's going to polarize it. So it's going to pull electrons towards that rod and leave a region of positive charge on the other side. So this is really a consequence of the conductor remaining an equipotential in the presence of an external electric field. So recall that the electric field is zero inside the conductor, and therefore these charges are going to get away from each other as far as possible. So consequently, that's going to create a dipole, and consequently a neutral conductor can still be attracted by the charge object. We've seen that a conductor shields an external electric field. So basically the external electric field bends to be perpendicular to the conductor's surface, and the conductor effectively acts as a Faraday cage with a zero electric field inside it. And this here is known as electrostatic shielding, where the electric field is shielded from entering the conductor. So electrostatic shielding can also be visualized by having an electric field due to a charge inside the conductor. So imagine that these are two conductors that are concentric with each other, and this is a section through both conductors. So the electric field due to this point charge is going to be radial, but bend to be perpendicular to the surface of the conductor. Okay, so it's going to look something like this. So it's more condensed near the charge. And this must be the case because there must be no electric field inside the body of each conductor. So given that there's no electric field inside the body of a conductor, then the electrons are going to develop on the surface of that conductor to prevent that electric field from entering the body of the conductor. So therefore, if you can imagine constructing a Gaussian surface through the body of the conductor, so this is a spherical surface, then the net charge inside that Gaussian surface is zero. So remember that the electric flux is the closed integral over that surface, and we integrate the dot product between the electric field vector and the area vector, and that's equal to the total charge enclosed in that surface on the permittivity of free space. So therefore the charge due to those electrons on the surface of the conductor is going to cancel out the positive charge, and therefore the net enclosed charge in that surface is going to be zero. So therefore the flux through that surface is also zero, and there's no electric field in the body of the conductor. Now due to electrons developing on the bottom surface of that conductor, so that's going to leave behind positive charges on the other surface of the conductor. And physically, the deficiency of electrons on that surface is modeled by positive charges. So therefore this conductor is going to act like a point charge, producing an electric field that emanates radially from it. So all around that surface. And consequently, electrons are going to be attracted to that positive charge. So you're going to have on the inner surface of the other conductor a bunch of electrons that are going to shield the body of that conductor from an electric field. So remember that the electric field inside a conductor is zero. And consequently, when you have those electrons developing on the bottom surface, they're going to leave behind positive charge on the other surface. So the net charge on this outer surface is plus Q, which is equal to this charge. And the net charge on the inner surface of this conductor is minus Q. And then plus Q, minus Q, plus Q. Because if you construct the Gaussian surface in the middle of that conductor, you have a charge of plus Q, minus Q, plus Q, minus Q. So the electric field inside the body of the conductor is zero. And that's the most important idea. Consider two concentric spherical thick shell conductors. The inner shell carries an excess charge of plus Q, and the outer shell carries an excess charge of plus 2Q. And we're asked to find the electric field for the following cases. So a conductor carries its excess charge on the outer surface under electrostatic equilibrium conditions. So therefore, the electric field inside the inner shell of this conductor is zero, and the electric field inside the body of the conductor is also zero. Now the electric field between the outer shell of this conductor and the inner shell of this conductor can be obtained by constructing a Gaussian surface that's at a distance r from the center. So if you applied Gauss's law, you'd obtain the electric field is 1 over 4 pi by the permittivity of free space by Q on r squared. Now because you have a positive charge on the outer surface of this inner conductor, then electrons are going to build up on the inner surface of the outer conductor, effectively shielding its body from this electric field. So therefore, if you construct a Gaussian surface inside the body of this conductor, the net charge inside that surface is zero. So therefore the electric field in the body of the conductor is zero. Because the net charge, due to the buildup of these electrons, is minus Q. And therefore at the outer surface of the conductor, you're going to have a deficiency of electrons. So you're going to have a net positive charge built up on the outer surface of the conductor. So that would also be plus Q. So therefore the net positive charge on the outer surface of the conductor is plus 3Q. And now if you construct a Gaussian surface outside this conductor at some distance r from the center, then you'll find that the net enclosed charge is plus Q minus Q is 0, plus 3Q. So therefore the electric field is 1 over 4 pi by the permittivity of free space by 3Q on r squared outside this conductor. So you can see that at points outside the conductors, the conductor acts like a point charge that's focused at its center. A solid spherical conductor with a radius r carries an excess charge Q. So this charge is carried on the surface of the conductor. Sketch the variation of the electric field and potential as a function of the distance r from the center of the sphere. While inside the body of the conductor, the electric field is 0, which you can verify by constructing a Gaussian surface. And then constructing a Gaussian surface outside the sphere, you'll find that the electric field is 1 over 4 pi by the permittivity of free space by the charge q on r squared. So that's for r greater than or equal to r, and therefore at r equals the radius of the sphere, we have the electric field is 1 over 4 pi epsilon naught by q on r squared, and it varies with the inverse of the squared distance from the center of the sphere. Now the electric potential inside the sphere is constant and equal to 1 over 4 pi epsilon naught by q on the radius of the sphere. So remember, the electric field is 0 inside the sphere. So that's for r is less than r. And thereafter, the electric potential is 1 over 4 pi by the permittivity of free space by q on r. So it varies with the inverse of the distance from the center of the sphere. A spherical conducting shell with a radius Ra carries a charge plus q and is suspended from another conducting spherical shell which has a radius Rb and carries a charge of minus 2q. So remember that the excess charge is distributed on the surface of the conductor. Now what is the electric potential inside the inner conductor? Well, we know that the electric field inside a conductor is 0 if there's no charge inside that conductor. So therefore the electric potential is constant. So all we need to do is find the electric potential at the surface of the conductor, and we have the electric potential at any point inside the conductor. So the change in electric potential is minus the work done by the electric force as some test charge moves from infinity to a point on the surface of the inner shell. So we can break this up as minus the work done as the charge is moved from infinity to a point on the outer shell, minus the work done as the charge is moved from B to a point on the inner shell. And this is divided by the test charge. So minus the work done by the electric force from infinity to B on the test charge is the electric potential at B. And we have minus 1 on Qt by the integral of the electric force, which is a test charge by the electric field, integrated over R. And we're integrating from the radius Rb to Ra. So therefore the test charge cancels, and we can write this as the electric potential at B minus, and the electric field is due to the charge inside the conductor. So that will be Q on 4 pi by the permittivity of free space by 1 on R squared. So we took the constants outside the integral. And now if we evaluate this integral, you'll get the potential at B minus Q on 4 pi epsilon naught, and we get minus 1 on R evaluated from Rb to to Ra. So therefore the minus sign cancels, and we know that this spherical shell, by Gauss's law, acts like a point charge concentrated at the center. So therefore the electric potential at B is 1 over 4 pi epsilon naught, and that's multiplied by the net charge, which is Q, minus 2Q on RB. So if we substitute into here, we get 1 over 4 pi epsilon naught by minus Q on RB, and then plus 1 over 4 pi epsilon naught by Q on Ra minus Q on Rb. And note that this is the change in electric potential as the charge was moved from infinity to the surface of the inner shell. And the electric potential at infinity is 0. So therefore we get VA is 1 over 4 pi epsilon naught, and then we have Q on Ra minus 2Q on Rb. Which is the electric potential at any point inside the inner conductor. Given the electric field for a long conducting cylindrical wire, which has a radius r and a uniformly distributed positive charge, find the electric potential at a distance r from the center of the wire relative to the surface of the wire. So we want the change in electric potential from r, being the radius of the cylinder, to some distance r above the wire. So that will be minus the work done by the electric force as we move the charge from R to R. And that's divided by the test charge, which is equal to minus the integral of the electric force, which is the test charge, by the electric field, integrated over R, from the radius of the cylinder to some distance above the center of the cylinder. And that's divided by the test charge, so we can get rid of it from the integral. So we have minus the integral of the given electric field, which is the linear charge density on 2 pi by the permittivity of free space by R integrated over R. So taking the constant outside the integral, we have minus lambda on 2 pi epsilon naught, and evaluating this integral gives the natural log of R, evaluated from capital R to small r. So therefore the change in electric potential between those 2 points is minus lambda on 2 pi epsilon naught by the natural log of R minus the natural log of the radius of the cylinder. So this is the same as minus the natural log of R plus the natural log of R. So if we apply our rules for logarithms, we get the change in electric potential between those 2 points is lambda on 2 pi epsilon naught by the natural log of R on R.